Okay, now we've thought about bolts in shear, we've thought about bolts in bearing, now we're thinking about ordinary bolts in tension. I'd like to introduce this by mentioning the requirements of the previous standard, BS 5950, and all I want to point out is that there were two methods in BS 5950. There was a simple method and there was a more exact method. So the simple method had restrictions on the geometry. So notice here that the cross-center spacing, or I would call that the gauge, was limited to a certain value. If we did that, then we could use a nominal tension resistance. And out of that expression, the most important thing is we're going to apply a factor of 0.8. Why do we apply the factor of 0.8? Because we're going to neglect, highlighted now, the prying force. So that was a simple method. Here is the restriction in BS 5950 that the cross centers or gauge could be no more than 55% of the overall width of the flange or the end plate. So it was a geometric constraint. If you wanted to indulge in the more exact method, then BS 5950 was going to talk to us about the prying force highlighted there, capital Q. It said that we had to include the prying force in the applied tension. If we did that, then down at the bottom, there was no need to apply this reduction factor of 0.8. So all I'm trying to do with that is introduce bolts in tension in the Eurocode and to say that BS 5950, the previous code, always had two methods. Simple method, apply the 0.8, a more involved method, don't apply the 0.8, but include in the applied load the prying force Q. What does the Eurocode say? Well, the Eurocode gives us a tensile resistance. So here is the formula. We know about the ultimate strength of a bolt. We know about the tensile area, so that would be the area under the threads. We know about gamma M2, it was 1.25 from the UK National Annex. We have a factor K2, unless we're using a countersunk bolt, then the factor K2, as specified in the Eurocode, is 0.9. So it's dead easy. So my favorite bolt, again, we plug in the numbers and out pops 141 kilonewtons. But the snip on this slide is from the Eurocode, and it says the applied tensile force should include any force due to the prying action. So really, this is telling us that we should be following the more exact approach. That's how it was described in BS 5950 and including for the prying force. This is the clause that particular requirement referenced, clause 311. So when fasteners are required to carry an applied tensile force, they must be designed to resist the additional force due to prying action. So the Eurocode doesn't really give us the simple approach, it gives us the more complicated approach. And it gives us a nice little drawing which shows the prying force. Notice it's the same nomenclature, capital Q. So the prying force we see is applied at the tips of the flange or the end plate, whichever it was. And if we resolve vertically, then not only have we got the applied tensile force, so that's up at the top, highlighted now, we've also got the prying force. So the bolts not only feel half of the externally applied tension, they also feel the prying force Q. That's why we should include it in the assessment. So here is kind of a plan view. Maybe one of these things is an end plate and a web, and maybe the other thing is a column flange and a column web, and we're pulling them apart, and we're seriously pulling them apart. They are pinned together with a bolt, highlighted now in the red rectangles, and eventually we know we're going to get some yielding. Maybe we're going to get some yielding close to the roots, so there, but we're also going to get some yielding on the bolt lines, because we know from the bolt lines going to the outside, we know that those plates remain in contact. So if I just take off my annotations for a moment and then look again, let's say at this left-hand side, we know we've got a yield line occurring on the bolt line. So we've got some moment there. We know that a moment is produced by the product of a force and a lever arm. So if we look on the left-hand side of this yield line, we know what the lever arm is. Therefore, we can back calculate the prying force. There must be a force there to give the moment which produces the yielding on the line of the bolts. And that force is called the prying force. It's to do with the lever arm, and you can imagine it's also to do with the geometric setting out of the bolts, which is why in BS 5950 there was that limitation about 55% of the width. So that opportunity to pursue a simple method was there in 5950. It was good physics. So therefore there is an advisory desk note, and here it is, number 354, which applies exactly the same rules that we used to find in 5950, but now presents it in Eurocode nomenclature. So we've got the same limitation over on the right-hand side, 55% of the breadth. And if we constrain ourselves to that requirement, then down at the bottom, highlighted now, we can pursue a simple approach, and that is to neglect prying, but limit our resistance to 80% of the full resistance. And I think, certainly in the United Kingdom, that's what most people will do, and that's what most people will prefer. They would prefer to not trouble themselves with prying. They would prefer the simple approach. And really, that's what we would recommend at the SCI. So, okay, if we did apply the 0.8 reduction factor, so there it is highlighted at the bottom, that 141 kilonewtons comes down to 113. So now a huge word of warning, ladies and gentlemen, because if you do look in the Blue Book or pretty much any other resources that tells you about bolt shear and bolt bearing, and in this case, bolt tension, the various resistances, notice that the tension resistance here, and this is from the Blue Book, is the, in inverted commas, full value, highlighted at the bottom now, of 141 kilonewtons. So if you're going to use this tabulated value of 141 kilonewtons, then you should be including prying in your assessment of the bolt force. So I really wish, ladies and gentlemen, when we had published the Blue Book, we had introduced an additional column. The additional column would have been the nominal tension resistance, and it would have been 80% of the values that you see on your screen there, just as a reminder to designers that there are two methods. And don't just blindly use the full resistance here. Certainly don't use the full resistance and neglect prying. If you use the full resistance, you must include prying. So you might want to make a very important note on this particular slide. I think it would be worthwhile to work out what 80% of these values are, and perhaps have those values stored in your memory banks, because really it should be those values that you want to use, and at the same time take the easy route and neglect prying. Should have mentioned over on the right hand side of this particular slide, there's something new and exciting for us in the UK. We never used to have this check, and this is punching shear. And this really is, will the bolt head or the nut of the bolt is in tension, will it pull completely through the material? I guess in the UK, we would always say no, because we never felt it was worthwhile checking that particular value. So, comment at the bottom of this slide, unlikely, we say in the UK.